So, hello everyone. I'm Balázs Majoros. Thank you for the introduction. And so, I've been working with Gábor Barnafeldi and Gábor Zero for around a year to tune the HIJING Monte Carlo event generator. And it's not working, sorry. Okay, I'm going to do this right here. So first, let's tackle the question. So why Monte Carlo event generators are important? So it provides a detailed simulation of high energy collisions, and it's widely used by both theorists and the experimental community. And it's very useful for designing new experiments and to make predictions and to put our physical models to test. So I'm sure everyone has seen a picture like this. Like it's a proton-proton collision in one of the colliders. And you can see that it's a quite complicated event. And this is a reconstruction of a Monte Carlo event generated event. It's reconstructed graphically. And so it is quite computationally expensive. As you can see on the next slide, I'm going to show you how, on the next slide, I'm going to introduce you to how some of the statistics, but let's go back once first. So HIJING++ is a Monte Carlo event generator for proton-proton and heavy ion collisions. It's currently pre-release, so it's under development. And that's why it's so hard for us to tune this system. It's the successor of the old HIJING, which was written in Fortran, and it's rewritten now in C++. And it has a native support now for CPU multithreading. And it's quite good for us because tuning would take eternity otherwise. So yeah, and you can see on the picture so how you can imagine a Monte Carlo event generator event. It's two nuclei collisions, and in the lower you can see a global model of the two nuclei collisions, and it's used to calculate several geometric quantities. And it's a very intricate system. It's very complex, and its output depends on several internal parameters. And we had to examine around 40 physical parameters, which are just the HIJING++ parameters. And these are theoretically not calculatable. So we had to use almost a better brute force algorithms or tasks to determine these parameters. And for one system, it's really easy to calibrate an event generator. I mean, one system is like a fixed energy and a fixed system for example, a proton-proton collision and for example, 5 analysis from experimental data. But our task is to find a working combination from a range of 20 giga-electron volts to 13 tera-electron volts in all proton-proton, proton-nuclei, nuclei-nuclei collisions. And this requires extreme amount of computational power. So the simulations took place in the high-performing computing clusters provided by the Wigner data center. And we have 7 nodes with 16-core Intel Skylake CPUs, and each of them with 32 gigabytes of RAM. And we can see some of the outputs of the HIJING++ in combination with the Rivet tools that it had to generate. And we have 5 terabytes of disk space, and in almost a year, so when I joined, this is the calculation that I took, we made around 22,000 HIJING++ runs and created, this is a very low estimate, but 340 terabytes of data. but it can be, I think around it's more like 600. This is a very low estimate in around half a year CPU time, and this is still not enough. So the tuning is still ongoing as we speak. There are a number of runs that are ongoing as we speak. So in the next slides, I'm going to introduce you to the tools and the tuning process of what you're taking. And so let's talk about the tuning process. First, we setting up the environment. I'm going to talk about each of them briefly, but there's a different slide for every one of them. So first, we're going to set up the environment and going to sample this parameter space that we chose. And after that, we're going to run HIJING++ for each of the parameters and going to optimize these parameters and run a validation and see if it's the expected. And if it's really good and all of our analysis is matching the experimental data, then we are happy and we exit the loop. But we stuck kind of here in this never-ending loop. So yeah. Okay. And so I'm going to talk about how we set up the project or the environment for the collision, for the simulations. And first, we have to choose the energy and the collision system and the experimental reference data. So after we've done that, we're going to figure out the most relevant parameters for each simulation and for this set of parameters. And less parameters equals less runs for us because we are not doing a brute force algorithm. So there is a tool that's helping us, which is called Professor. And I'm going to go back one slide. Professor is a parameterization-based tuning tool. So the more parameters we're going to give him, the more runs we have to make, and it's one sample can take days or weeks to run. So it's quite an important aspect to just choose the the more important parameters. And there's also the reverse toolkit that we're using. It's a set of experimental data analysis, and it's another tool that we just pipe our HIJING output into, and we can get some nice YODA files, which are core of the reverse toolkit. It's basically a better histogramming tool, and of course we're using the HIJING++ to run the simulations. So after we've done after we figure out the relevant parameters, we have to find a good sampling range for each of them. And this can be quite tricky because if we randomly choose a sampling range, then one parameter can be very sensitive and all the rounds can be like nonsense, and we have to depend on previous runs or some physical parameters, which we discuss. Yeah. So after that, we're gonna write some scripts to run the Monte Carlo event generators, and we're going to do an example at 5 teraelectron volts with the lead collisions and with this rivet analysis, which is going to be the charge particle, cellular rapidity, density, and centrality classes. And we're going to do a little bit of tunings ourselves. So after we've done after we choose the parameters, we're going to sample the parameter space, which is done by the professor. And we're gonna end up with different configuration for the HIJING++ in each subdirectory, and we're gonna we're gonna run the HIJING with the rivet. So this is like the run command. And after we run the HIJING++ with for each subdirectory, we end up with a format like this with our outputs. And depending on the sample size, it can take days or weeks to run a sample. And after that, you can run the professor's optimization tool, which will give us the resulting directory, which contains the predictions for the generator and the results. So there are lots of intermediate steps involved. So we're gonna make a parameter interpolations, and we're gonna run a sensitivity plot to see which parameters are more sensitive, and so it's quite a lot of tasks. And finally, we call the professor tune, which gonna give us this with a weight file. So with the weight file, we can specify which experimental data is important for us, and we can tune the professor tune to tune the experimental data. So it's quite tricky, but we have to do that. And after that, we try to find the best fit and continue with that parameter set. So this is like the output. So this is what the professor gave us for their predictions, and this is the output of the professor. This is just basically a text file with the minimization results and the parameters that it's concluded on. So I'm going to show you another tool that is currently developed, which is a machine learning based optimization tool. It's quite similar to the professor, which is a per bin model, and it uses a feed-forward neural network for each bin, and it's training it with a gradient-based algorithm, and it can use the same sample as the professor, so it's quite good. The tuning step is also the same. It's to minimize this chi-square function, and it's going to end up with our results. So I'm going to show you the validations and the comparison of the two optimization tool. So for reminder, there's the energy that we use, the system, and the analysis that we tuned to, and you can later see the experimental analysis on the HAB data. It's public. So we had 6 parameters within these ranges, and the professor it's quite not quite equal. So there are like some of the parameters that they are quite close, but this is, and we know that this is a very sensitive parameter, and it's quite different. So we expect a very different results from this, and we can see that the professor and the found 2 of the upper bounds of the ranges. So maybe we have to recalibrate and do this run all over again with different ranges. So after this, we run the HIJING++ with the given parameters, which the MCNN tunes and the professor gave us. So with the black dots, you can see the reference data, and with the blue line, you can see the professor, and with the red line, you can see the MCNN, the machine learning based tools prediction, and you can see that it's quite not really in touch with the reference data. That is because maybe it needs a lot more data to train, and the professor's prediction is not quite good as well. So this is where we stuck in. So in summary, in the validation runs are in favor of the professor, but it seems that the MCNN tunes needs more data, and and we have to do this all over again to do this to make to maybe have better results. And NCNN tunes is other drawback that is a machine learning based tool, so it needs a lot of training, and it's a bit slow. It's quite slower than the professor. The NCNN tunes it was for me around 3 hours to optimize. Professor was like 10 minutes on a CPU, but the hardware probably can take care of this problem. So currently the HIJING++ is in this state, and hope it's going to release soon. So stay tuned. Thank you for your attention, and special thanks to the Wigner GPU Laboratory and Wigner Data Center for providing us with the hardware and the support.
Okay, thank you very much, Balázs.